Currently locally.
If not, I'll share my screen.
You're in a meeting. What's the meeting ID?
Oh, you in, Tom?
Yes, I'm.
Oh, you're in. Okay, good, good. Excellent. It was a while ago. I mean, did you send me your report? I mean,
No.
Hey,
send it to
JP.
me now, please.
That one. It's six.
Active test can write your thesis.
3
9702
9702
4950.
4950. Is it John Fall or John F?
All
All right.
You prefer John Paul, so.
Yeah.
Can you mute your microphones now? And can everyone online hear us? All right. Your mic.
You too, John.
All right. IT support.
Okay. Let's see here. Okay, should I start? Introduce you first. Everybody is here and pleasant. Thank you. Thank you everyone for coming to see Alexandre's master's thesis presentation on obstacle detection using the Evo platform. Go ahead.
Thank you, John, and thank you everyone for coming. So my name is Alexander, and I will be presenting my master thesis, obstacle detection and tracking using a LiDAR for a hydrofoiling unmanned surface vehicle. First and foremost, let's get to know the vehicle which motivated this project. So Evolo is an unmanned surface vehicle, meaning that it operates with no humans on board. It is also a hydrofoiling vehicle, which means it flies a few centimeters above the water surface, making it very agile and efficient. Therefore, it's ideal for many maritime applications, all the way from environmental monitoring to security and defense. Let's see it in action. This is Evolo moving. As you can see, it operates in environments where obstacles are, for example, buoys, short or tall, moving boats, the shoreline, which can be very complex, and many other things, for example, rocks. It's an unstructured environment. So the mid to long-term goal with Evolo is to make it an autonomous surface vehicle. And one important step in order to achieve that is to know where obstacles are in order to be able to avoid them. And this motivated this project, where we will be developing a real-time perception system that will support a future obstacle avoidance implementation. In a maritime environment, the optimal and collision-free safe trajectory does not only depend on where obstacles are currently, but it also depends on where they are heading, as there are various types of moving obstacles, for example, boats. And for this reason, we not only need to detect obstacles, but we need to track their motion and be able to then predict their future position. So we'll be using a LiDAR to detect the obstacles, which is a very good sensor with a high resolution, which can detect even small obstacles in close, mid, and even long-range applications. In order to track and map the obstacles in our environment, we will need to join several LiDAR scans over time. And as the LiDAR is mounted on a moving platform, which is Evolo, we need Evolo's position estimate, and that is obtained with the inertial navigation system here, which is the SPG Ellipse D, which both are connected with VOS2. The LiDAR uses light beams to detect obstacles in an environment, and it therefore creates a point cloud, which represents these obstacles. In a maritime surface environment, the water surface is very reflective. And this leads us to one of the challenges that we have to face in this thesis, which is the LiDAR will detect some water surface. This is actually our main challenge. You can see in this picture, Evolo is driving in that direction in a narrow canal underneath a bridge. And you can see the point cloud includes the canal, the bridge, but also a lot of water detections. And this makes detecting buoys and short boats very difficult because they look like water surface detections in wavy scenarios, for example. In this thesis, we have developed a novel water surface filtering strategy that actually got very good results to solve this challenge. Besides solving this challenge, in this thesis, we also want to understand how a LiDAR can detect and track obstacles in a marine environment, and if it is even a suitable sensor for this application. Let's get to the methodology and the results. So in this thesis, we want to take a 3D point cloud that comes out of the LiDAR. And of course, if we are detecting the water surface, which is not an obstacle, we need to filter it and pre-process it. And for that, we also need the localization and attitude estimate from Evolo. This module, this first module, outputs a filtered point cloud in 2D. And why 2D, you might ask? So Evolo can only be controlled and follow trajectories in the surface of the water, which is effectively a 2D environment. And for this reason, we can use the assumption that Evolo operates in 2D, making all our future computations much faster. We'll use these filtered inputs as, of course, an input to several methods I will be comparing. All of these create a probabilistic representation of the obstacles in the environment, and they build that belief over time with several filtered inputs. In order to compare them, we have defined a set of system requirements that we need to follow. And one of those examples is requirement 4, which means that we have to be able to deal with occlusions. With Evolo, while turning, we can achieve high roll rates. And while doing so, the LiDAR can, for example, be only seeing the water surface and the sky. And for that reason, we still need to be able to avoid obstacles. And so we need to be able to keep a representation of the obstacles that are currently occluded. We will discuss all other requirements later on. But let's get to data acquisition, which will enable us to verify these requirements. We went with Evolo and we gathered a lot of data with ROS bags, and we divided into the 4 operational environments where Evolo operates: a narrow canal, a sparse scene, a marina, which is quite the opposite of a sparse scene, for example here, and wavy scenes, which really test our filtering strategy. And besides it, we set up a very cool experiment where we drove Evolo close to a boat, and we got the GPS position of that boat. And that enabled us to get a ground truth position of an obstacle in order to validate how well our algorithm will track the obstacle. And the output of that is, for example, here, we can see Evolo is moving, and this is the point cloud that Evolo is estimating. And that point cloud includes waves, and here it's detecting a boat, which we can see it's there because we have the GPS position. We now get to the first module that I told you about, pre-processing and filtering. So our goal is to take a raw 3D point cloud and turn it into a filtered 2D point cloud, which we also call a laser scan. To do that, we first take the point cloud, and please watch this image, and we filter it, removing water detections, noise, and other things, and we keep only the obstacles. Then we project all the remaining points in the point cloud, the filtered one, into a 2D plane, and we select the closest one to our sensor. If we do this for the entire horizontal resolution of our LiDAR sensor, we effectively get a laser scan that represents all the obstacles in the environment as well as the 3D point cloud did, but we get a 99% data reduction, which really makes algorithms faster. But how did we do that first part of filtering? We did it in 3 steps. So we first remove the water surface, we remove points that are too high, for example, bridges, and we then remove any noise. The first part involves detecting the water surface and removing any points that are at the water surface or below it. To detect the water surface, we use an IMU inform ransack. This means that we take the roll and the pitch from the IMU to estimate which points in the point cloud correspond to the region where water should be. We then use ransack to estimate the most likely plane where the water surface is, which is this blue plane you are seeing here. It's the estimated plane. We then remove things, and we do so by only removing points up to a 30-meter range, because while watching the Rosbachs in this thesis, we understood that the LiDAR mostly detects the water surface up to that range, and this really improved our results. You can see in these results, here we are filtering out all the water detections, but we are keeping the boat here. And here the same thing. The white points are what we are keeping, and we are keeping the shoreline here and here, and we are also keeping a few buoys that were here, but we are removing all the water surface. So these results were great. But you might be asking, what about after that 40-meter range? For that, water detections are very sparse, and they can be filtered out with common point cloud noise filtering methods. For example, radius outlier filtering. This only keeps points that have enough neighbors around the specific radius to them. And results to this were also very good, and it really improved the results from the ransack method. You can see here, without the dynamic radius outlier filtering, after some time, we start getting a few points that should have been filtered out and worked. And in this second image, we see that those were correctly filtered out using this method. As far as we know, we were the first ones to use this phenomenon of 30-meter range with dynamic radius outlier filtering, and it really improved our results. So now we have the first module done, and we have the filtering data, the filtered data set. We'll use this as input to several methods that will construct a belief about obstacles in the environment over time. We will now explain this, compare them, and conclude on which is the correct option to support future obstacle avoidance. The first one is local occupancy grid mapping, where we take the filtered laser scan that I just described it to you, and we build a map that divides the world, a 2D world, into grid cells. And in each cell, we build over time a belief of how occupied that part of space is. And if we see it as occupied many, many times, it becomes black, which means it's occupied. There's an obstacle there. If it doesn't, it's white, and it's a free region of space. And results for this were very good. You see here, Yvonne is driving again in the canal, and there's a boat passing. And we can see we are filtering out some water detections, and we are considering most of the water as free, which we should, the margins of the canal as occupied, and we can actually see that we are correctly considering the boat region as occupied. This was great, and it was only possible because we tuned it to update our occupancy belief very fast because of possible moving obstacles. If you look better or in more detail to this data set, we can also see, for example, in this middle picture, that the LiDAR cannot see this side of the river, the left side of the river, because it's being occluded by this massive boat. And inherently, our method does not update that region, and thus can keep the same belief that it had a few seconds ago of that space being occupied and free there. And this effectively deals with occlusions. But there's one thing, this method does not estimate any velocity of any obstacle in the environment, and that's where it falls short. And for that reason, we developed the second method, which excels at exactly that. So multi-obstacle tracking is very good at defining the velocities of the obstacles in our environment. It does so by clustering the obstacles in the environment, and it tries to track each of these clusters with a common filter, which estimates the velocity of that obstacle. A cluster can, for example, represent a buoy, or can represent a boat, or any other obstacle. We then draw a bounding box around these obstacles, which will be the occupied region of space, and knowing the velocity of that obstacle, we can predict where they'll be in the future. And this is very promising. The first results we got from it in a sparse scene are amazing. We see Ivo is here driving, and there's a boat to the right of it. And we see there's a bounding box completely enclosing that boat. And there's even a velocity vector here in blue, which means that we are correctly estimating the boat to be moving in that direction. We can also see there's a buoy there that's static, And we can see that there's a bounding box in red as well around the buoy and no velocity vector, so it's static. And that's great. We used the GT dataset that I told you about a few minutes ago to validate these results. And we got an average tracking precision of 2 meters. And we did so in 96% of the frames that we tested, which is great in terms of results. But there's an issue with this method. So when we get to nearshore environments, it's very hard to cluster the shoreline as different obstacles and to try to enclose them with bounding boxes. You can see here, there's of course an issue. If this is considered as an obstacle, all these points, then drawing a bounding box around it will include parts of the free region, which is the water, which we don't want. And here it's Evolo entering a marina, and it's a very complicated image, and that's the point here. This method fails to represent complicated scenes or near-shore environments. So therefore, it's not robust to support future obstacle avoidance. But what about if we merge the best of both worlds? If we are able to track the boats that are moving with bounding boxes and estimate their velocity vector, and we map the static parts, for example, this marina, that will get us a very good approach to solve this problem. To do so, we clustered, again, the input filtered clouds, and we classified each of these clusters into static or dynamic. Static clusters belong to objects that are standing still, and dynamic clusters belong to objects that are moving, for example, a boat that's moving. And so we mapped with static obstacles, and we tracked dynamic obstacles. And our output is the overlay of the two. Of course, the secret here is how did we segment the two? And we did that with two methods. The first one tracks all obstacles, and the ones that show a velocity estimate that's below a certain threshold are static. And the second method is inspired by a paper published last year that solves this exact problem for a maritime environment scenario. And the results were impressive at first. We see here, there's Evolo, there's a boat to the right of Evolo that's being correctly classified as dynamic, and there's a bounding box with a velocity vector there, which is what we want. And here's a buoy that's being tracked, that's being mapped as static, and this is what we want. The thing is, both of these segmentation methods that we tried were very sensitive, not only to Evolo's localization precision, but also to the speed and size of obstacles and to tuning parameters. And we couldn't find a configuration that segmented all clusters well. This means that we have a lot of scenarios, for example here, where Evolo is driving and we are classifying the shoreline of the river as static, which is good, but we are also classifying a moving boat as static, which is not good at all. And so we here also consider that this method is not robust. And it is not robust because I cannot guarantee that in nearshore environments, we won't have shoreline being tracked as a bounding box, which is a no-go. So we've developed the methods and we have discussed all about it, but which one should we choose? None of them fulfill all the requirements. So here we'll be comparing the methods and we'll be analyzing if the LiDAR is a suitable sensor for this application. We'll start with the second issue. Is the LiDAR a suitable sensor for this application? To validate that, we define the first requirement, which is we need to detect all obstacles with a minimum of 65 meters in range. Why? Because we calculated that value when for a situation where Evolo was driving against, for example, a wall, and we need to start our avoiding maneuver at least 65 meters before we get to that obstacle. And we went to the lab, and in a very long corridor there in Técnica Ringa, we put a small obstacle, the size of one of the smallest maritime buoys, for example, and we understood that at 65 meters, the LiDAR can still detect enough points, meaning that it wouldn't be filtered out by our filtering strategy. And in conclusion, LiDAR is a suitable sensor, and our filtering and pre-processing strategy is also suitable to support obstacle avoidance. Let's now move on to the other requirements. In terms of the third one, we need our full perception pipeline to be faster than the output frequency of our LiDAR. And this is achieved, the LiDAR outputs at 10 Hertz, so we have a maximum requirement of 100 milliseconds. I try to optimize the code, and for example, for filtering plus building the occupancy grid map, we on average only take 45 milliseconds, which is well within the requirement. In fact, all of our pipelines were within the requirement. And now we will need to analyze the other requirements. And we have done so kind of during the presentation. And the main takeaway here for the 4 last requirements is that object tracking and that full segmentation pipeline are not robust. And they are not robust because in nearshore environments, we cannot guarantee that they will correctly represent the environments to be able to avoid them after the obstacles in order to avoid them. And for that reason, our proposed solution is to use the local mapping. The main limitation here, of course, is that it does not predict where obstacles will be in the future, but it still enables for some more simpler obstacle avoidance implementation on Evolo. I also want to say here that the success of this method is largely due to the robust filtering pipeline that we implemented. And this is arguably the most important and impactful contribution of this work. And you might be asking, okay, so how do we use this for actual obstacle avoidance? That's the main question here. My answer and my suggestion for future work is to use a local path planning method. This can take Evolo's current position, it can take a goal position, for example, a GPS waypoint, and the local mapping that we are estimating, and it can produce an optimal and collision-free trajectory that takes into consideration the dynamic constraints of Evolo. And to conclude, I want to summarize the contributions of this work. We have developed and validated a real-time perception system that can support a future implementation of obstacle avoidance. And in order to do so, we have developed a novel LiDAR water surface filtering strategy that combines these 2 methods, which were, as far as we know, not combined before this work. And we actually got very good results for it. We validated these implementations with data that we collected from the real world using Evolo. And for that, we had to set up and integrate sensors on Evolo with ROS2. And we also developed a digital twin of Evolo in a Unity simulation. This was very important for debugging our code, but above all, it will be very important when testing and debugging obstacle avoidance before going out on the water. And with that, I want to thank you very much for having listening to me. And I'm very eager to answer any of your questions.
So, turn out to the and Tom.
Yes. First of all, thank you for the very clear presentation. It was very easy to follow. And yeah. My first question is, what do you think about the feasibility and the utility of merging a different sensor, having some sensor fusion system? Would it add something and makes some of the steps easier, or do you think the LiDAR is optimal alone?
So, in terms of sensor fusion, there has been work that has shown that the camera fused with the LiDAR can improve these results, mainly in the parts where we need to filter out the water surface. This is mainly because the water can see or have an idea of where obstacles are and where water is, and therefore it can help the LiDAR understand if he's missing some obstacle that's not being detected or not. So in terms of sensor fusion, I would say that, and it would definitely improve our filtering results.
My next question was, in the beginning, you mentioned that if you have some roll on of the Evolo, the LiDAR will be limited in its in what it can see. It will see more of the less useful things.
Yeah.
Do you think it would be useful to mount the sensor on like some kind of gyro, or if it's even like realistic to do that?
Of course, it would help things out. In this thesis, we have considered the role in the pitch in our methods. So if we look back at this slide, the first thing we do when we get the raw point clouds, and we use the roll and the pitch that comes from the IMU, and we transform the point clouds to a base footprint frame. This means that a base footprint frame, for instance, is a projection of the position of Evolo into a 2D plane. So it only has X, Y, and yaw. And while doing this, we are correcting for any roll and pitch. But what you were asking, as far as I know, is would it help because we would see more obstacles?
Yes.
And we didn't have those problems while developing this. And Evolo tends to roll a lot, but during short periods of time. So our belief of where obstacles are, for example, with the local occupancy map, is enough to not need a gyroscope.
Yeah. Okay. It's very clear. If in the scope of this study, low profile or submerged obstacles were not part of the scope, but in terms of future work proposals, do you have any ideas of how one could begin to do that? Because obviously it would be necessary in a fully functional system.
Okay, so I'm not sure. I'm gonna the picture here, which helps. So Evolo, this vehicle, it drives with just a few centimeters inside the water. It's not like a normal boat, as it uses these foils to fly around and create lift, just like an airplane. The section of it that's underwater is very limited. I would say that our approach cannot be directly adapted to understand underwater obstacles, and that's also was not the goal of this thesis, because the main obstacles here to avoid are the ones above water, because Evolo operates above water and to the surface of the water.
Yeah.
A possible solution for what you just said was to consider a pre-made map that usual boats use when driving around, which includes the depth of the water in several areas. And using that, we could have an idea of how deep the water is and try to avoid areas which were not deep enough for Evolo to.
Okay. Nice. How robust is the water plane filtering across different sea states and different speeds of the?
That's a good question. So to answer it, I'll tell you what we did. So Evolo drives up to sea state 3, which means waves around a meter high. We didn't get any data sets that is as rough as that. We tried, but we couldn't get those. But the most wavy data set that we got is exactly here. When we were driving just behind the moving boat. This is the GT data set that I told you about in the beginning. And here's a boat moving in the front, on the picture on the right. And Evolo was driving around in the middle of the waves that this boat was producing, and they were big. And you can see here that we were very successful at filtering out this all these waves and just keeping the boat. So as far as we know, it can deal with the most rough situations that we faced. There are sometimes, for very rough seas, some points that are not greatly filtered out and just still appear, because we are using the assumption that the water surface is kind of a plane and we remove a region close to that plane. So there are situations where a few points can appear, and that's why we need a probabilistic method to represent the environment after filtering so much. I actually have another thing to add to that exact answer, which relates to these results. So we tried actually two methods, and before we came to the IMU Inform RunSAC, we were just filtering out the water using the roll and the pitch estimate to estimate the plane. So without using the RunSAC part to estimate the most likely plane. And you can see that in this very wavy data set in the bottom, we were not able to filter out all points. There are some waves here that are produced by the boat that are so high that we consider them to be obstacles. They are actually almost as high as the boat itself. The magic of RunSAC is that it uses all the points to estimate the most likely plane. And it can be a plane that's kind of tilted to include all our visualized points from water surface. So that's why it's so good, this RunSAC method. It's nice.
Is there a way for you to report some kind of certainty measure from the obstacle detection to the planner? Because then it could take more conservative decisions based on the certainty of the obstacle estimates.
That's very hard to do.
Yes.
That's very hard to do because we have only one system to perceive the obstacles. And currently that system doesn't really evaluate itself. The only way I would say we can do that is if we were using the multi-obstacle tracking pipeline. And as I told you, this uses Kalman filters to track each of the obstacles. And Kalman filters have a covariance matrix when estimating the position of each obstacle. That means that if the covariance matrix of our obstacles would be too high, we can feed that in to the planner and say, be more conservative, increase the safety margins. But again, that method does not fulfill our requirements, so I don't recommend to use that. So for the mapping situation, there's not a method to solve that.
Okay, my final question. If you had less processing budget, what parts of your pipeline would you either cut or maybe optimize further?
That's actually a great question because that's the current issue.
Okay.
In Evolo, currently we are using a very big computer with batteries, and that's very heavy to support all of this pipeline. Moving forwards, we want to remove that and process the sensors with a microprocessor in there. And for that, LiDAR is not a feasible sensor. It's very heavy. The current resolution of our LiDAR is 2048 by 128. So it's thousands of points. It's massive. And a microprocessor could not at all deal with that. And we are doing the best that we can to reduce the data as soon as we get it. So while filtering, we are already reducing the data by 99%, then is computation. What I can tell you is if we change sensors, for example, to a radar that has a lot less resolution, that could be done. And we actually have tested exactly that. A few months ago, we were out testing Evolo, and Jacob got me a radar from a car, which produces a much lower resolution image from the environment. And we validated if it still detected enough points. It's hard to say if it does. It did detect the main obstacles, but the resolution is very, very low. Our filtering strategy could then be adapted to work with less points, and it would make a difference. I have actually here some data to justify that. Give me a second. Here. So we ran a lot of tests trying to understand how long it took our computer to process these pipelines for several different scenarios. And for example, let's focus on the top left one, which is point cloud pre-processing, the filtering step, which is the most important one. And we can see that for sparse scene, it takes very little time. It only takes 11 milliseconds. So if the environment cooperates, our filtering step could be adapted for a lower power computer. The rest of them are kind of hard to do so. And let me just add, sorry, by making this answer very long, we have also created a solution to use this exact method. I'm not sure where I have it. So basically, if we have still a powerful computer on board, that could process the incoming point cloud and produce a filtered one, we have actually developed a very low resolution range bearing representation of the environments that can be actually transmitted to our low power microprocessor that can then do the control part.
Okay.
But in that case, we would have a big computer either way.
Okay, thank you very much. Very good
Questions?
answers.
Yeah, yes.